I guess Arya is here, so she's from group 1, I guess. Chetna is also.
Chetna is not. Chetna is there. Yeah,
Yeah,
maybe.
Chetna just she joined. Chetna, can you hear us?
Yes, sir, I can hear you. Sorry, I joined late. Did you mention anything?
Yeah, we were discussing. So maybe you can share your result, or maybe the problem you're facing, like in some of the experiment, or especially in this.
Okay, it was regarding the H1. So we have just started with the analysis of H1.
No. GMRT data.
Yes. So, okay. Okay, I'll share the screen in a while. Wait.
Screen sharing has been enabled. Chetna, you can do that.
Yes, sir. Actually, one of the students will share the screen and he has not joined yet. So I've messaged him to join it right away.
So other member from your group?
The others are not very good with programming. So it was me and Dipradeep who were doing it today morning. And he's joining.
He's joined. Yeah. Okay.
Dipradeep, can you share the our program for the H1 centimeter line that we were doing in the morning? So we will.
Actually, right now Ruta is there, so it's Ruta's project that we wanted to discuss.
Meaning ours was with Subhashish Roy, sir. So. Hmm. Okay, no. Yeah. No. For GMRT, we don't have any doubt as yet. Maybe we can jump to the next group.
We have also kind of almost sorted out the GMRT part, except that some the students were uh, asking about during the discussion yesterday. They were asking about cross correlation and auto correlation, which I kind of did explain to them. So I think they should be able to sort that portion out by today evening, as far as the GMRT data is concerned. So maybe I can ask, they are here only, I can ask Himadri or Sahil if they want to particularly clarify anything from Ruta, then they can do that.
My primary doubt was the autocorrelation and the cross correlation. So when we do the autocorrelation, we will take the modular square of the one signal only. And if we want to do the cross correlation, then we should multiply the two signals, right? This is the process.
So have you taken the Fourier transform already?
No, not. I mean, first we analyze in voltage time, then taken the Fourier transform. Then
you need to take Fourier transform to get the spectra, voltage spectra for the two things that you want to correlate.
Okay.
And then multiply channel by channel the contribution of one with the complex conjugate of the other.
Yeah, I think that part we have reached till that part till Fourier transform is was sorted out. So where they were actually stuck yesterday was the difference between. So I was telling them that when they take cross correlation, then after that they don't have to do then they don't have to do the modulo square after that. So that's where we were discussing.
That's correct. And there you might want to treat the real and imaginary parts separately. Okay,
Yeah,
while teaching also.
yes, that's exactly what we wanted to discuss. This part when you were saying that you have to treat the real and imaginary part separately in that case.
Yeah. Or you would like to compute the magnitude and phase based on whichever looks more meaningful and representative, okay, informative, you can do that. Remember that while displaying, you might display amplitude and phase separately, but the averaging has to be done in the real and imaginary part separately first, and in the averaged output, you can decide to represent the real and imaginary part separately as a pair or as a magnitude and phase. You should not average the magnitude and phase uh, separately. Okay, it's always the real and imaginary parts. The complex information is averaged, and then for representation purposes, you can compute the other pair like the magnitude and phase. You should never average the phase.
Okay. Okay.
Yes, so after the Fourier transform that you have already done, so what you did for autocorrelation using the same signal, basically you use the Fourier transform of the same signal. You just have to use the Fourier transform of the other signal and get the cross correlation.
Yeah. Right. Yes.
Yes, yes. Thank you.
Thank you. I think with that, I think we'll be able to do that after that. Thank you.
Regarding Ruta's experiment, some of them might have joined late, so they may not know the context.
Anyone? Khushi, Pranav, Roshan, Saksham.
So actually one thing I can mention here, that this fifth part in the uh, basically the file that I had given, you need not wait for all the intermediate 3, 4 to be done. So fifth part can be done as a separate thing um, after you have done the meaning it need not wait until you do all the steps up to fourth one. So you can attempt to see what you find in terms of the relative importance of phase and magnitude in the data. Yeah, please go ahead if anybody was wanting to describe what they've got.
Yes. Uh, Jahan, you may explain if you have some problem.
Yes, thank you. So I don't have much of a doubt, just a few minor things. Ma'am, as you have shown in the demo video of this experiment, actually I compared my dynamic spectrum of cross correlation with that spectrum you shown in that. And I suppose my spectrum is reversed. So do we have to do the time reversal in this or not?
Is there a time reversal or a frequency flip?
I suppose time reversal probably. Actually, yeah, what I did was for that till the dynamic spectrum, I just copied the code of the ORT for that and just adjusted a few parameters. So in ORT, I've done the time reversal already. So for that, for GMRT, I have got the reverse time spectrum. So I suppose it will.
No, is it the reverse time axis or is it reversed flipped frequency axis?
No, time.
Time cannot get reversed very easily because you will be sequentially analyzing the data. That
I mean, I'm just
arrow,
asking that do we
that
have to do time
direction is
reversal
very
in this
difficult to change.
experiments or not?
Hmm?
Do we have to are we supposed to do the time reversal thing in this experiment or not, as we have done in ORT?
No, did you do time reversal in ORT? There is no need for time reversal. You might have done the frequency axis flip,
Sir,
if at all.
sir, but in the telescope, we get the latest data at the first, and then
Which one? No,
in the
you will get the data in the sequence of time as it progresses.
okay, right.
That cannot be changed, but you might have sometimes a Fourier transform instead of a forward transform, an inverse transform done. Okay, or you might have a genuine flip of the band before it is recorded, the information is recorded. In those cases, you might need to effect the flip of the frequency axis.
Okay, in this the collab file for the ORT that Prakash sir provided, that it is written like you may see a reversed pattern. This spectrum may be flipped. So it is like in the frequency, not in the time.
Correct. It's
That's
always
Yes.
in frequency. Time you can you will have to do something extra to reverse the time order because the data are written in the time order itself, and you will be processing them one after another in some sequence.
okay. Right. Right. Okay. So that.
Yeah, so in the case of, I think it is like to convert it to like the actual frequencies, like right now you may have like 0 to 200 megahertz. So if you were to actually convert it to the frequencies, then the order of frequencies has to be flipped in the case of GMRT. Um, but I think all of you are plotting between 0 and 200 megahertz, or you're just using the channel numbers,
Yeah,
I
in
suppose.
the ORT, we have plotted. I mean, I have plotted dynamic spectrum as the from 0 to like 16.5. But when we do
Hmm.
this, we have to go to the actual frequency as the
Hmm.
also depends on frequency. So absolute frequency.
Yeah, so here also, if because we are not doing that part, there
Yeah.
is not much meaning. We haven't included the step to go to the actual frequencies. But if you were to go, then for band 3, your center frequency is 400 megahertz, and it is increasing in the reverse order. So the channel numbers increasing in one direction, 0 to 2048 or whatever you have chosen. The frequency basically is flipped.
Okay. Right.
Except the strange thing about Python plotting is that it doesn't put the two origins associated with the two axes together. So it flips the y-axis where the top left is marked as 0, okay,
Yeah.
for the y-axis value, and then it runs into higher positive values downward.
Yeah, you have to specifically
Might be another
choose
source
it.
of confusion while comparing two diagrams. Okay.
We have to set the origin basically to lower, I think.
Yes, yes.
So when you're comparing it with some other similar picture, please take this into account while comparing.
Yeah,
And
yes, sir. Yeah, that's more probable that I've mistaken there. Yeah,
Yeah. No,
I will
except for
look
the
into it.
flip, other features should be relate meaning. If you
I
flip
mean,
it,
the other features like the lines and the symmetry and all that were similar.
no, the particular places where you get RFI, the frequencies at which you get RFI, and so on, should roughly correspond
Yeah.
to across the pictures.
Yeah. Okay.
Okay, good.
Thank you. Yeah, it's clear, I suppose. Okay, sure, I'll do.
So Ruta, you have suggested them to estimate the expected RMS divided by observed RMS even for the other experiment where only 1-bit data are taken and or only
I
amplitude.
think for the
Right?
1 bit data, I have mentioned only to compare, but the same exercise actually can be done there.
That will help them to quantify and assess
Hmm.
what the level of improvement or degradation that has occurred due to 1-bitting. Apart from seeing the overall uh, shape of the spectrum and so on, which will be hard for them to comment on, if they calculate
Yeah.
this efficiency, which is the observed RMS, expected RMS divided by the observed RMS, they would see a drop from normally it should be close to unity, that ratio in the absence of RFI. Here they should find it dropping to 0.67.
Hmm.
In fact, that's one way of making out what kind of digitization has taken place.
Yeah. So actually, so this fifth part actually, although it is sort of numbered, and that's why I wanted to mention that that can be done um,
Yeah, independent.
anytime. Yeah, independent of the others. I just realized that maybe
Yeah,
some
you're right.
groups may wait until they finish everything until that part.
Correct.
Yeah.
So we are working on the dynamic spectrum, and as of now, we don't have any doubts. So if we get any doubts, we will let you know.
Yeah, I think so far I have seen band 3 dynamic spectra. Has anybody looked at band 5 data? Meaning the same step, just replace the files and you have you looked at the dynamic spectrum for band 5? because that comparison you can make out some things just by looking at the spectrum. So if your codes are sort of ready and you can make cross correlation spectra, just use all the data sets and try to create the dynamic spectra for all of them. Yeah, correct. Yeah.
Yes.
Actually, I wanted to ask about the channel number and frequency. Like, do we consider the numbers from 0 to 2048? Sorry, 0 to 2047 in that case? Hello,
Yes. So
am I
if
audible?
you, yes, yes. So if you've taken a 4096 point FFT,
Yeah.
so you can uh, plot it as a function of frequency on the x-axis or the channel number. So channel number is just the, let's say it's just a series of numbers actually, because that is the number of points you will get if you choose the positive part of the frequencies. You will end up with that many number of points, and that is your resolution. Basically you cannot, because you have not sampled your signal enough to get any more resolution in frequency. um, so it is basically you will have to anyway construct that x-axis and then plot. So these 0 to 2047, those are the channel numbers.
Okay, so like they are like kind of references that we use to classify our signal, right?
Yeah, those are
Yeah,
the
it is just numbers to
frequency.
refer.
And ma'am, like we are facing a problem in writing a code for like color mesh, like taking an input for it, or I am sure, even I am sure. Like yesterday, Prakash sir told about the theoretical concept behind it, but we are unable to convert it in code. So, like, any suggestions for it?
So sorry, converting which part to code?
The final part of second, like plotting and heat map, wherein x-axis is frequency, y-axis is time, and
Hmm.
z-axis is the signal.
So for an
We did
like,
get physical.
hmm. So
No, I'm
I
just
myself
telling.
have
Yeah.
used ImShow. So that takes the numbers, and then you can provide um, the frequency and time, and it will plot. So I can I don't know, maybe Prakash, if do you want to add something, I'll.
Yes, sir. Okay, sir, I will check it again. And like, if there's any problem, yeah. Yes, sir. Yes, sir. Yes. Yeah. Sure, sir. Thank you.
So you have made the other plots, I suppose, the plotting the spectrum, just
Yeah.
let's say the
Like
y-axis and
yes.
those plots you have made.
Yes. The yesterday I like showed like it was weird graph in Slack.
Okay, yeah, I remember that.
So initially it was quite weird. Like when I considered inverse of time to be a x-axis. Like took an variable fm which is equal to
Hmm.
1/tn, and I plotted the graph with fm at x-axis.
Hmm.
So it was totally weird. Yes, sir. Yes.
Yeah.
Yeah, so for actually plotting it, your array will only be, the values of the z-axis essentially. Okay, and the actual numbers on the x and the y-axis will be just serial numbers.
Ma'am, in that case, I got an error like saying that the expected value was 2, but they are getting only one value.
Yes, that was for columnish or something.
Yeah, 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 for
Actually,
column.
that I have not used, so I don't know what that error means. But in ImShow, if you so just like what Prakash just now showed, so that matrix itself just contains the numbers or uh, whatever are uh, the number of points along x and y axis. Both are basically that's the two-dimensional array. So it just contains the z axis essentially.
Okay.
Okay, and then when you plot it, the serial numbers essentially, because you have, if you have used the full file, you have 1024 such spectra, the timestamps. It will basically make the x and y axis. So for ImShow, you just need to provide that matrix, and then it will be plotted, and you have to convert the you can yourself convert the x and y axis to actual frequency or uh, the timestamp, the actual time in seconds, or by multiplying that number.
Okay.
So see the shape of the or the characteristic of the matrix that you are trying to provide to ImShow. Then you will understand what it is trying to plot, and if at all there is error, why it is giving an error.
Okay, ma'am. Thank you, ma'am.
Ma'am, I have a question.
Yeah, go ahead.
Yeah, so ma'am, in the PDF which you shared, it is written that in 1.1 it's written compare the mean and the RMS for the values in the parts where there is saturation and where there is no saturation.
Yeah.
Does this saturation and non-saturation means while plotting the histogram where the value is maximum and the non-saturation is where the value goes to just minimum? Is it like that?
So if you look up if you plotted the time series,
Hmm.
uh, just amplitude versus the voltage versus time,
Yeah.
then you would have noticed that there are portions in the time series where most of the values in that particular time um, are going up to the maximum or the minimum.
Uh, Ma'am,
So
I
the
can't see the minimum points, but yeah, I can see I plotted the data from 0 to 1000. So like there was only one point where it was going to minus 120
yeah.
something.
So if you consider very short instances of time, like
Okay.
just 1,000 points or so, then you will not find such too many such points. But
Okay.
if you plot all the points in the time series,
Mm-hmm.
then you can find out the portions where many points are going near the saturation and the time instances where essentially none of the points go to the saturation value. So
Ma'am,
saturation means that it is going, the values are basically being cut off. So essentially, there is a this plus my 128 to minus 128 limit within
mm-hmm.
which the data are recorded. So
Mm-hmm.
anything which basically which is going beyond that value, it's like if you plot the whole time series, you can see that as if somebody has clipped the time series at
Yeah,
that
yeah, yes, yeah, yeah,
y-axis value.
yeah,
So
yes, ma'am.
that is what I meant by saying that that is where the saturation is happening.
Okay.
So the basically saturation means that the whatever device or whatever you are using to record the values is
Mm-hmm.
unable to record the actual value. So it will
Okay.
just report a saturation value. So wherever what is its maximum or minimum point that it can record. But the
Okay.
actual value can be higher or lower than that. So
Mm-hmm.
that is why it means that the system is saturated and you are unable to measure beyond that limit.
Mm-hmm.
So it's just like it just clips the signal.
So, ma'am, okay, so I understood this part that what do you mean by saturation, non-saturation. But, ma'am, here it's written compare the mean and the RMS for the values. But, ma'am, what I can look from this plot is uh, uh, like nearly 50% of the plot is saturated.
Yeah, so you can look at meaning I don't know if you have plotted C11, C12 or whichever the if you
I
plot the
plotted the
entire
C11.
yeah if you plot the entire time series and not just limited number of points, then you will find that there are portions where significantly one can make out the so I can I don't know which is the data set I have used, I'll just tell you. So this okay, I think it is more very obvious in C12 in the underscore 4 data set. If you take that C12
I
data,
haven't used the underscore data.
so there things are little more obvious. So if you
Okay.
plot the full time series, then you will see that there are extended portions along the time where there the values are not reaching saturation and
Mm-hmm.
where there are values reaching saturation very often.
Yeah, yes, ma'am. So,
Like,
ma'am, but
maybe about one third of the data has saturation in the beginning, wherever the
Hmm.
yeah,
saturation
yeah, yes,
is
sir.
there, and then the middle is quiet, and then it
Yeah,
again
yes,
it's
sir. Yeah, 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 yes, sir. Exactly. I have the plot like that only. So, how do we actually calculate the mean and the RMS for this? I'm not getting that part. So, is it like do we because I don't know like how to put this, but I I couldn't understand that part.
So let's say you are averaging over 10, 10 let's say 50.
Like it's completely colored in blue color, like the
Hmm.
default color, and after that there are like peaks, and then like it's not completely covered in the color, and then after
Hmm.
that a small portion in the last is also completely covered
Hmm.
with the color. So, which means that the mean should be 128 or like nearly 127 to 128 only.
No,
No, no.
assuming that it's occupying equally all the values between the two limits, that will decide the mean. The appearance at the face of it might look like that. It's not that it's a straight line hovering at the top, which would have given the 128 as the mean.
Ma'am,
It's occupying the full range, but not allowing for excursions outside that, right?
Yeah,
That will not
yes.
imply the limiting value as a mean.
But sir, technically, sir, shouldn't the limiting value should be the mean, because like after
No,
like
because they're in between values also. You're not seeing a straight line stuck to the top or bottom, right? You're seeing in between values also, but you're not seeing excursions beyond the limiting values. So, which will not represent the signal properly. That's all there is. It doesn't say anything immediately about the mean that you will get. Okay, from the appearance in the 1D plot of time series.
okay, so
If you plot the
okay, sir.
distribution of it, then you can infer things like what you are inferring right now. Okay.
Okay, sir.
Sir, in this case, is it fine to consider a threshold value? And if the value is greater than threshold, then form a different array. And if it is less, then form a different array and work accordingly.
This is for which purpose?
The thing which I guess Sahil was trying to say, the
No,
first part.
no, you can retain the values as they are represented. They already have the limitation that is understood or stated. Okay, and we
No,
want to see its effect.
I mean to classify the signals which are in saturation and which aren't in saturation.
You can, I think, if you just make a histogram, you will see enhanced population at the limiting values. Okay, that might be a better judge without even viewing it by eye. If you make 3 sections of this data and make histograms of values, you will find there are in the saturated regions, the frequency of occurrence of the limiting values is very high, whereas values don't reach that high in the unsaturated distribution.
So then same will be applied for the RFI part, right? Wherein we need to classify between RFI and the actual signal.
That is done by comparing the mean and RMS, expected RMS divided by the mean observed RMS. This is even in the case where nothing was saturated.
Okay.
Sir, I had a question regarding this part. So when we calculate the RMS for the unsaturated part of the time series graph, we see that it is somewhere around 19.5. I'm taking like this C11 data, and the saturated part is also the unsaturated part is 19.5 and the saturated part is 22.6. There's not a lot of difference in the RMS values between them.
Yeah, there may not be huge difference in the RMS value, but the distribution functions would differ quite significantly.
Yeah, they do, because in the unsaturated part, the mean is about -1, whereas in the saturated part, the mean is about like 0.1.
Because even in the unsaturated part, one tries to use the range, available range optimally. So often the overall range is within few standard deviations on either side. And so the values will be typically like the ones you mentioned.
Okay, sir. And why are we subtracting the mean from the entire data series? Like, is that just to enhance the signal?
No, the mean before Fourier transforming is subtracted only to remove any artifact of the digitizer input.
Okay, of the
Having a
instrument.
discrete pedestal.
Okay.
It is not expected, but sometimes malfunctioning or whatever inadequate care in the electronics might result in a small DC pedestal, which might give you a constant value addition to the true signal that you are trying to digitize.
Sir, so whenever we take a Fourier transform, is it always preferred to have the data series mean as near to zero? Like, or will it always?
It depends on what you're looking for. For the sky signal, we do expect no contribution at zero frequency. Okay. Or even if it's there, it is not very useful because it has the aliasing from the positive negative frequencies. So the typical two end frequencies are often confused with alias contributions always.
Okay.
Even if they had a meaningful number there, without any contamination of the DC pedestal, they still remain unusable for any astronomical measurement purposes.
So I think that is the reason why when I was doing the ORT data, I did not subtract the mean. So there was a huge peak at the zero frequency band, which I think should not have been there.
Yeah, all that is done in the direct voltage data. After that, subtracting the mean has a different meaning, and you have to be careful about it.
Okay. Thank you.
Yes, sir.
Mohammed Saad has some issue with the mic. He can type if he has any question.
Yeah, I'm just reading that. Yeah, so maybe you have read or you have come across the definitions of autocorrelation and cross correlation. So the Fourier transform step basically makes it easier for us to get to the autocorrelation or cross correlation. So there one can do it even without without FFT, but Fourier transform gives a very easy method to get to the autocorrelation and cross correlation. So see, with Fourier transform, so you have one signal, let's say C11, you have taken 4096 points and you have Fourier transform them. So you have this array of these complex numbers now, and you can take the absolute value and square it. So squaring in the sense that we want to multiply the signal of the same Fourier transform with itself, basically for autocorrelation. So if you have A as the Fourier transform, then you just do A star A to get the autocorrelation. Whereas in the case when you have two different signals, like you take 4096 points of C11 and Fourier transform it, call it A, and then you have C12 when you take 4096 points, Fourier transform it, and you call it B. Then you take A star B basically. So rather you may want to call it a B star. So it is just the let's say, so that is what will give you the autocorrelation and cross correlation. So after FFT, your job is just to multiply the two. If it is the same antenna, then you will get autocorrelation. If you have the FFTs from for the two different time series, you will get cross correlation.
I might just want to add one word to the entire description. You will get cross correlation spectrum or autocorrelation spectrum, so that the domain confusion that people might have might get removed. Autocorrelation spectrum is equivalent of a power spectrum. Cross correlation spectrum is equivalent of cross spectrum. Which are respectively Fourier transforms of the time domain autocorrelation function and time domain cross correlation function, which is measured as a function of relative lag in the time domain.
Yeah, so we finished with the ORT data and we just started the GMRT today morning. So yeah, I don't really have any doubts as such. Like we've done up to Fourier transform and then we'll do the autocorrelation and cross correlation. So as of now, we don't have anything to ask.
Hello, sir. Can you hear me? Hello, sir. Hello. Hello. We are working on the GMRT data right now. The doubt I have faced was I plotted my cross correlation and sorry. Yeah, I actually plotted both my cross correlation and autocorrelation graphs, but I couldn't. There was not much of a difference between both of them. There were minor differences, but I was confused whether I was on the right track or not. I actually confirmed it with Ruth Amaya today morning. She said it was okay.
Yeah, so the high points that you find in the dynamic spectrum,
Yes, ma'am.
those are typically like from RFI, uh, because of which the amplitudes are very high in those channels.
Okay.
So, but some of it either will reduce in its amplitude, or you will see some differences like that for the some of it may already go away as compared to your autocorrelation spectrum.
Yeah, I noticed that my cross correlation but spectrum has less
Yeah.
noise actually.
So there will be differences, but nothing, you won't see it like a completely different picture or anything. But that's the idea. You make out where are the differences and where are the same similarities.
Okay, thank you. Understood.
And for a quick comparison, you might want to average it across time and represent the spectrum and then compare.
Sure, sir. I'll do that. Thank you, sir.
That might make your comparison easy.
Yeah. Please feel free to find ways of what you might consider a comparison. So this is you can average across time and compare the spectra, or you can average to some extent, not fully, but let's say every 10 spectra or something, and then compare. So you can choose and see what you get.
Sure, ma'am. I'll try that. Thank you.
Yeah, excuse me, I am from group 9 as well. We want to know whether we should add pictures of the experiment in the report as well. I took some pictures of the setups. So should we include that in our report? Okay, thank you, sir.
Yeah, so if there aren't any other questions, I'm fine. Just to remind that the number 5 need not wait until you finish everything else. If you've got your codes until Fourier transforming and dynamic spectra, you can definitely go ahead and try out the 5th one and try to see what happens when you just retain the sign of the voltages and use that versus what happens when you remove the sign and use the magnitudes to do the same process. So, yeah.
Hello.
Yeah.
Yeah, I'm from group 3 actually, and some of our members didn't join a bit late. So, from group 3, for the GMRT data, we have reached till the power spectral density for the entire data, and probably we can work out the dynamic spectrum by today. And just out of curiosity, I wanted to ask that whether GMRT has any pipelines or servers where we can get the dynamic spectra or the plots using some bash commands or anything. Yeah.
Um, so there are a number of tools available to play around with the data, but the data that we are using in the school right now, that is a very, let's say, a special kind of data in a sense, because we are trying to understand what actually the GMRT correlators do. Okay, you are doing the autocorrelation and cross correlation, and you have used directly the voltage data. So typically when astronomers observe, this voltage data is actually already processed by the GMRT correlator, and what you will be given in your data file is typically the visibility. So it is basically you will get your visibilities as your data, and unless your experiment specifically needs recording the voltages, because this voltage recording has to be done at Nyquist rate. So these are like nanoseconds recordings. So this is very expensive to retain. It takes a huge amount of data space and it just cannot be recorded. That is why in our experiment we are actually looking at this data to understand what exactly happens inside the GMRT correlator, and trying to understand already beforehand, before your data gets processed and averaged out to much lower time resolutions. So Nyquist rate is the highest, let's say, sampling rate at which you can attempt to actually find the properties of the RFI. Because once you, let's say, I gave you a time series now, which is a average time series to, let's say, several microseconds order, or milliseconds. So you will lose the information in the process. So the GMRT data that we are using here in the school is quite a special data set to understand the concepts of what goes into processing the data. But if you take any typical data set towards some pulsar, or towards any interferometric observations towards any particular field, any galaxies or clusters, etc., you will typically process the visibilities and get an image. So there are a number of tools to work with visibility. So things like APES and CASA, these are the softwares which people use to process those data. But for just the voltages parts, typically the tools are similar to what the kind of codes that you are already writing. So I don't know if you meant that, or does it answer your question?
Yeah,
Or
yeah,
was
it
it?
answers. Yeah.
Yeah, so our
Because
data set is special in that way that we
okay,
are trying to do the thing by hand, which is actually already done by the GMRT correlator.
okay.
But the advantage of this is that we are looking at the RFI as it comes in and at the highest time resolution where we can actually see it.
Yeah, right. Because for pulsars, especially for pulsars having only a few milliseconds of time period and comparable
Hmm.
pulse widths, the Nyquist sampling will be sufficient or insufficient. Means will we require more rate or something for these pulsars?
Yeah, so pulsars, millisecond pulsars. So only when one took data at that rate could one discover millisecond pulsars. So in case if there are any transients or other other objects which actually have pulses at much faster rate than millisecond pulsars, for example, then definitely one needs to just keep on going to higher sampling rates and see if there are any such phenomena. But maybe physical models, some theoretical models may have predicted.
Okay.
So
Thank you.
the sampling rate can limit your ability to how fast a transient can you actually detect.
Right.
See the voltage data, there is no choice but to sample it at the Nyquist rate associated with the bandwidth. Okay, regardless of what phenomena might be buried in it. It is only after you convert it to intensity that you have the choice of asking what phenomena you want to be sensitive to and take the time scales associated with whatever phenomena you're looking for and sample adequately finely to sample the details of that phenomenon, be it transient, be it pulsar signal.
Okay. Yeah, thank you.
Ma'am, actually in the graph which I showed you yesterday, like I again plotted the same. This time I'm getting a graph similar to sync function. So like, is it fine?
Have you put it on Slack or?
No ma'am. Shall I?
You can check because I'm not exactly sure what you mean by seeing a sync function.
Okay, a minute, please.
I have a general doubt regarding the RMS. Hello.
Hello.
Yeah.
Yeah. I have a general doubt regarding the RMS. So, like, in this case, like, for calculating the RMS in any radio data, like, do we follow the usual definition of RMS, or do we take the mean and divide it by the number of samples, square root of number of samples?
Your last part was, couldn't be heard well. Were you asking about the normalization?
No, I was asking about RMS. So yesterday I've checked few definition of RMS for radio astronomy, and there they took the mean of the data and then divided by the number of samples. But
no,
that is not the actual definition of RMS.
Yeah, mean is mean. I mean, if you sum the numbers and then divide by the number of such points summed, you will get the average or mean. But even the RMS has an implicit word which is not normally spoken, is the root mean square deviation from the mean. That from the mean is not always stated, so it is implicit. So what you are expected to do is, after estimating the mean, you're supposed to estimate the deviations from it, take the square of it, sum it over the ensemble, then divide by the number that that you used, number of such samples that you have used, and then take the square root.
So that's the usual definition of RMS. Like we take the mean of the squares and then divide it by a square. Then take the under root.
Correct. So it's that's the correct usual definition. Only thing I was adding to that is it's a root mean square deviation from the mean. That from the mean is implicit.
So there's a
Deviation is not from zero.
So do we mention how much is the deviation, meaning 3 sigma, or how much on either side of the mean? Or do
So
we take...
so that is already estimated for sample to sample. And then you get the mean measure of it, which is called the RMS, which is equal to the standard deviation itself.
Because like if we have a voltage series, for example, and we create a histogram, suppose the bandwidth is, the frequency is going from 0 to 10 hertz, suppose, whatever energy range. So if we take the spread in this range and in a narrower band, say a window of 4 to 8 hertz. So that will give me a different RMS. So how do we calculate variability? The entire range or a subset of that?
At the level at which you are doing this analysis is either in the time domain where the raw voltages are available, or in the frequency domain where individual channel data are taken and a time sequence of it is analyzed. Correct? In which case the bandwidth is already committed to the channel bandwidth, which is the entire bandwidth divided by the number of points you have across the spectrum. Which is something that you would use in estimating the expected RMS, where the mean divided by square root of time bandwidth product you would be taking, right? And the time bandwidth
Because
product
yesterday
with
also
the
I asked this thing.
Yeah, sorry. Go ahead.
Because yesterday also I asked this thing and I tried the standard deviation upon square root of number of samples. So deviation between north and south aperture in the UT data should be within that range, meaning is expected to be within that range. But those numbers were not matching.
So the mean is a proxy for unaveraged ensemble. RMS of unaveraged ensemble. From that, when we begin averaging, we reduce it by the square root of the number of samples averaged, right? That is what will give us the expected standard deviation. And this we divide by the observed standard deviation, which is computed from the ensemble itself by the arithmetic that we just described.
Okay. Sorry, Bipradeep, you were asking something. Is it clear to you as well?
Yeah, so basically, we are using the usual definition of RMS.
Bipradeep,
And for calculating. Hello?
Yeah, we can hear you.
Yeah, so basically for calculating the RMS, we are following the usual definition. And for the spread, we are using the mean divided by the square root of the number of samples.
Yeah, the mean can, if you wanted a mean to RMS ratio, you can retain it as it is. The meanings of mean remain. If you wanted to know the expected RMS, you can use the mean and divide that by the square root of time bandwidth product to get a measure of the expected RMS. If you were to just construct a mean by RMS ratio and plot it, please go ahead and use the normal definition of mean and normal definition of RMS.
Sorry, I lost you in the middle. What did you say?
All that I'm saying is, if you were to compute expected RMS, then you can take a help of the mean and divide that by the square root of the time bandwidth product. Okay. But if you were to make a plot of simple mean divided by RMS, use the simple definitions of mean and RMS and use that arithmetic to compute them separately and take the ratio. There, the time bandwidth product does not come in.
Okay, thank you, sir.
I just want a clarification on the FFT of this spectra. So do we take the Fourier on 4096 points and then add them over an average over all the rows? That is, I think there are 1024 like rows of the data.
You need to retain them separately to construct a dynamic spectrum.
Okay.
And you would like to, at the first opportunity, you would like to take the modulus square of it, if you are looking at the autocorrelation spectrum, which means power spectrum, so that averaging will not kill the signal. Okay. because there will be uncorrelated contributions from one spectrum to another spectrum with zero mean. So you would first like to get the power spectrum, and then you're allowed to average power spectra over duration of interest, and such multiple durations will make you get the dynamic spectrum over so many samples, average samples, which you can use for each channel to get an ensemble to compute mean, RMS, and so on. And please remember that to compute mean and RMS, the native accuracy of it or uncertainty associated with it depends on the size of the ensemble. So if you make too few spectra in your dynamic spectrum, you will find the 1 upon square root of that number is going to be rather high. That means fractional uncertainty in the mean and RMS calculation is going to be large. So you would like to have, typically about 1,000 such average spectra.
Okay. So while
I want to ask one thing at this point, since you were talking about this, Desh. So this we would see when we look at the power density, the point that you just said, when we look, this will be visible in the power spectral density in the shape of the spikes. The point
more than in the shape of the spike, in the general fluctuation level that you will see.
Yeah, that's exactly what I meant. So in the general fluctuation level, this the point that you
look
just
very
made,
noisy.
Yeah,
It will look very noisy when you haven't averaged enough.
Yes.
Okay.
Yeah, right.
And it will also be apparent when you compute the RMS and mean and then plot that. You will also find the uncertainty is there from channel to channel, more than what you would have expected. The smoothness is not as high as you would expect because of the uncertainty, but here it will be a fractional uncertainty.
Yeah.
So it will not be readily apparent, but the initial lack of enough averaging would show up as a first glaring level of noisiness.
Yeah, okay. Thank you.
Hello, am I audible?
Yes.
Oh, okay, it's fine now. I had a slight doubt in the ORT data, like I mentioned about the contrast problem. So actually what's happening, it's the same piece of code, and when I give the values of the north antenna, so the in the dynamic spectrum, the amplitude at the pulse, it comes out about 0.5. I mean, I normalized it from 0 to 1, the amplitude. So it comes about 0.5, the pulse, the amplitude at the pulse. And for the south antenna, it comes at about 0.8. So what happening when I'm giving AN plus AS, in the south antenna, the surrounding noise has more than the pulse in the north antenna. So that's the contribution of the north antenna is getting completely disappeared in the AN plus A combined dynamic spectra. I mean, so if there could be any reason for that, because I'm using completely the same code. I mean, there's no difference. I'm just giving AN, then separately AS, and then I'm giving AN plus AS for the same.
Yeah, so the variety of reasons why signals might appear different in the two halves of the antenna, but they are unlikely to be so dramatically different. It is possible that one path is more noisy than the other, and that you can assess by, or even the gains might be different. So the best way is to compare the overall average of the two and make a comparison of the overall strength of the noise across the spectrum. Once you bring them to the same scale by appropriate factors that you can use to multiply, then you begin to compare the pulsar level of pulsar signal in the two.
Okay, so I should kind of normalize between the northern and south, both the poles.
Yes, make them roughly equal. Okay, the one way of doing it is simply take the after removing the mean in the voltage data, take the standard deviation in the two. Okay. and to make them equal, or to make them unity or whatever you want, common scale, scale one with respect to the other, and then you begin to compare your uh, details of the pulsar signal.
Oh, okay, okay. Yeah,
That
that's
might
actually.
help a better comparison than this. And also in doing that, there could be slightly different spectral structure and so on based on the phase relationships and the gains across the band. So you might find it useful to actually construct a de-dispersed pulse sequence from both and then make the comparison and see how similar or dissimilar they are.
Okay, okay. And one more doubt I had from Prakash sir. So, like for calculating the dispersion measure, so what I did, I actually in the dynamic spectra, I plotted a grid and then kind of manually got the points and roughly calculated. So, I mean, has anyone opted, I mean, an automatic method like using the code only to get the dynamic spectra? Because I did it manually, like plotted a grid and then calculator obtain 2 points and then calculated dynamic dispersion measure manually. So has anyone done it like automatically, like putting it in the code and then obtaining it? Because the value seems off. I got it about 60. I got the value of 60. So and it was about 67.7, I guess, in his PPT.
Even I did the manual calculation and I got a DM of about 72. So
It's interesting that you mentioned these two values. It already shows the uncertainties that can result from the way of measuring the DM based on these. Because remember, there's only certain accuracy to which you can pinpoint the timing and measure the relative delay between the 2 points at corresponding to the two frequencies. And if you enable that mentally and put a measure of that, you will find that none of the deviations you have seen would be surprising.
We got DM of around 108. So how are we supposed to know that the DM values are correct or not?
Yeah, so the DM value is correct when you get the maximum signal on alignment, when you apply that DM.
So can we just, I mean, for getting a more clear picture on the DM value, we can sample random points and then calculate the DM value and take a mean?
Yeah, random points is not a good strategy. You can take a systematically increasing value in certain range. For each one of them, you can compute the mean profile, measure its height, or have a measure which is sum of the squares of the intensity across the pulse window, and then see where that measure maximizes, for which DM the measure maximizes. And this is professionally what pulsar astronomers do to find out the correct DM.
Okay, thank you.
Okay, so with the DM of about 72, I got a pretty much aligned de-dispersed spectra. So
Right.
yeah, but also when I integrated over the frequencies for the single frequency time spectra, there was more noise in my spectrum than the one you had shown yesterday. So maybe I will try to make it a bit more. Yeah, so the dispersed spectra came pretty much aligned, but with a DM of 72. But the single frequency time spectra that I had to compute after that, that was actually that actually differed from the one you showed. It did have a bit more fluctuation towards
Yeah,
the
because it has
lower
not
part.
benefited from averaging of all the channels. Uh,
No, it did, but it uh, did still have a bit of noise. So.
no, so which one are you comparing, and which one was worse signal to was which had more fluctuations? A
No,
single time
the
sequence from corresponding to a single channel, or something else that you're referring to?
no, I'm talking about after de-dispersion, the pulses that we're supposed to.
Yeah, after de-dispersion, do you combine all the channels to get
Yeah,
a single time sequence?
yeah.
Okay, and then you're comparing that with?
Yeah, I'm not. I'm comparing that with the one Prakash showed yesterday in his presentation. So it has pretty much the same shape, except a bit more fluctuations towards the.
Yeah, did you have similar averaging in the time domain, like 50 or 60 spectra, power spectra averaged to get about a millisecond resolution, or
Yeah,
different?
yeah. I averaged over 50 spectra. Okay. Yeah, maybe. Yeah.
Yeah, but primarily it could be the reason that Prakash just mentioned, because that itself could make a factor of root 2 in the contrast.
I see. Okay.
Sir, am I audible?
Yes.
Sir, I wanted to ask a question referring to the color mesh only. Like the input which we consider there is a 2D array, and it's related to autocorrelation. So the autocorrelation array which we get is has dimensions of 1 is to 1 into 2048. So do we need to convert that 1D array into 2D array? Like exactly what we need to do to form a 2D array?
Are you doing a autocorrelation function just in time?
No, sir. In Fourier domain, the taking of the squaring of the part, the absolute value.
Okay. And so you get a power spectrum after that?
Uh, Whenever we do autocorrelation, so the array which we get is has the shape of 1 into 2048. That is one row and 2048 column. So
Correct. That becomes
uh,
one column, and you stack such columns, right? It becomes a 2D array.
okay, so we need to stack such 2048 columns, right? Sorry, 2048 rows, right?
2048 point column is
Yeah.
placed next to each other to gain the dimension in time, right?
Okay. So it's like first we consider first 2048 points, then plot for it, then again consider
But you
next
might want to
2048.
take the power spectrum and average it with the successive such spectra to gain one column. Okay. But if you don't, then yes, you stack such successive results from the patches of whatever 4,000 whatever points, right? From which you get whatever number of channels you get,
So
and those
sir,
columns are stacked together.
we
Correct.
need to just divide the complete data in the patch of 4096 points, right?
Correct.
Okay. Okay. Actually, that's what it was confusing me. Thank you.
Can we have a short break of 5 minutes before reassemble? Yeah.
Yeah.
Thanks.